deriving the arc length formula. Okay, so let's just say that we have some curve right here. Let's call this just a row, just so we can visualize it better. Okay, so let's say we have this point S0, S1, S2, S3, and then all the way to Sn. Okay. So now what we can do is we can kind of approximate it by drawing the lines from each point. Okay. So yeah, we can kind of draw lines, right? Okay. So now we can label this. Let's draw our little axis. So we can write this, say, S0 is A, S1 is X1, is X2, so on and so forth. Okay. Now let's look at this point, S0 and S1. Alright? If we draw the lines connecting it, it's a triangle. So let's we'll just draw a close-up picture of it. So we would have this curve, that. Yeah, curve, the line, and the triangle. Okay. Now this triangle can be described, let's call this delta x, because x is changing to x and the delta y. So let's call this delta x and delta y. Okay. And then this can be delta s. Okay, so the length, so length is equal to s. Okay. Now we can approximate, or actually we can give delta s a value. So you can set delta s is equal to si minus si minus 1, or si minus 1. Okay, so say this is S3 minus S2, okay? So we see this delta S is pretty much a hypotenuse, right? So we can approximate delta S squared. So delta S squared is approximately delta X squared plus delta Y squared. So if we want to get delta S, is approximately equal to the square root of delta X plus delta Y, right? Or delta X squared plus delta Y squared. You can write that, but the squares cancel out. Okay. So now what we can do is, since this is an approximation, but calculus is all about the infinitesimal, so we can write this as in terms of ds, dx, and dy. So this will actually give us the length of it. So ds is equal to the square root of dx squared, or you know what, no, we'll get ds squared is equal to dx squared plus dy squared. Okay. Now, this dx squared, and dy squared, the ds, dx, and dy are all one thing. So it's not d of s squared, it's just ds squared. So it's the infinitesimal space squared. Okay. And then we can rewrite this out and take the integral. We can write this out. So we'll get, take the square root of this, and the integral, we'll get s is equal to the integral of square root of dx squared plus dy squared. Okay, there you go. Alright, this can also be another variant, so it could be this ds is equal to the square root of 1 plus dy dx squared and dx. Okay. So let's look at this a little more here. We have this dy dx, this can be combined. So that's just a derivative. Okay, so final form you'll mostly see during lectures or maybe your homeworks. You'll see s is equal to the integral. This can be from a to b. If we have bounds, it'd be from a to b of the square root 1 plus dy dx. But in this case, you're going to do Newton's form or notation, which is f prime of x squared dx. Okay. So, alright. This notation I like the most. If you're getting used to it, this is probably the best notation. But in textbooks, so let me just write in textbooks. You'll see the notation S is equal to the integral ds. So it's pretty much this, but just shortened out. So hope this video helped you. Make sure to like, subscribe, and comment down below. Have a great day.